Okay then. So now when it comes to linear algebra, as I said, we'll be getting around 2 to 3 marks from this linear algebra. And if you see about the topics in linear algebra, so we are having three major topics in linear algebra. So the first is about matrix algebra, and the second topic is about linear system of equations, and the third topic is about eigenvalues and eigenvectors. Right, so these are the three topics what we are having in this matrices or linear algebra. And when it comes to the matrix algebra, we'll be having about multiplication, and we'll be studying about the determinants, and we'll be learning about inverse of a matrix and rank of a matrix. And in linear system of equations, we are having non-homogeneous and another one is homogeneous linear system of equations. And when it comes to eigenvalues and eigenvectors, we'll be learning about the properties of eigenvalues and eigenvectors. And we'll be learning about Cayley-Hamilton theorem. Right. So these are the topics what we are having. And if you ask me, the main topic is about your eigenvalues and eigenvectors. Okay. And if you are from mechanical, then no doubt there will be a question in linear system of equations. And if you are from civil, then you can expect a question on rank of a matrix. And this eigenvalues and eigenvectors is common for each and everyone. And we can't guess like which problems will be coming. And but if you ask me about the linear algebra, so these are only the 7 topics what we are having. But I can say for sure that without eigenvalues and eigenvectors, so far I have not seen any gate paper. Okay. Right. So now when it comes to the matrix algebra, as I said, we'll be studying about the matrix multiplication. Right. So the matrix multiplication is possible when A is of order m cross n and B is of order n cross p, then the result will be of order m cross p. And the matrix multiplication is possible only when number of columns of A are equals to the number of rows of P, right? And again, one we can say is matrix multiplication is not commutative. Now, what do you mean by commutative? There is AB is not equals to BA always, except for few matrices. And even we can say that matrix multiplication is associative. Now, what do you mean by associative? That is, A into BC is equals to AB into C. And in order to compute the product, so the number of multiplications required will be M into N into P, and number of additions will be M into N minus 1 into P. Right, so this is about the matrix multiplication and some of the properties of the matrix multiplication. And again, when we talk about the matrices, like say if I'm talking about a matrix or especially about a square matrix. So when we talk about a square matrix, so then we can say there are two types of matrices. One is a real matrix and another one is a complex matrix. That means if all the elements of the matrix are real numbers, so then it is a real matrix. And if all the elements of the matrix are complex numbers, so then we say it is a complex matrix. And like in real matrices, whenever A transpose is equals to A, then we say A is a symmetric matrix. And if A transpose is equals to minus A, then A is a skew symmetric matrix. And if A into A transpose is equals to A transpose into A is equals to I, then we say A is orthogonal matrix. Okay. And in the same way, when it comes to the complex matrices, so what we'll be saying about the complex matrices is, like say if I'm having a matrix A as 1 plus I, 2, 3I minus 4. Let us say this is a complex matrix. Now, if I replace all the elements with the conjugates, that is 1 minus I, 2, negative 3I, and negative 4. So this matrix, we'll be calling it as conjugate matrix. And if I transpose this conjugate matrix, that is A conjugate whole transpose, then it is 1, negative I, negative 3I, 2, and negative 4. So this we'll be calling it as the conjugate matrix, and that will be denoting with A theta or A star. Okay. So now whatever the properties that we had discussed about the real matrices regarding the transpose, the same properties we'll be discussing with the conjugate. Like say, if A star is equals to A, then we say A is a Hermitian matrix. And if A star is equals to minus A, then A is a skew Hermitian matrix. And if A into A star is equals to A star into A is equals to I, then we say A is a unitary matrix. Remember, unit matrix is different, unitary matrix is different. They both are not same. And again, like if A square is equals to A, then we say the matrix A is idempotent. And if A square or A to the power P is equals to O, then we say A is a nilpotent matrix. And if A to the power 2 is equals to I, then we say A is an involutory matrix. And if A to the power k plus 1 is equals to A, then we say A is a periodic matrix. And here k, we'll be calling it as a period. And here in the nilpotent matrix, P, we'll be calling it as index. Okay, right. So now, whenever we look into some properties of this symmetric and skew-symmetric matrices, now when I talk about a skew-symmetric matrix, so like if I'm having a matrix A, N, and the elements are of the form Aij, if Aij is equals to I to the power k minus j to the power k, then the matrix A is always symmetric. Sorry, skew symmetric. Then A is always a skew symmetric matrix. And for any skew symmetric matrix, sum of all the elements of a skew symmetric matrix are always zero. And the trace of a skew symmetric matrix is always zero. Okay. And similarly, if I'm having a matrix A, An is any matrix or any real matrix, let us say, let's stick to the real matrix, then A plus A transpose, A plus A transpose is always a symmetric matrix. And A minus A transpose is always a skew symmetric matrix. And every matrix can be uniquely expressed as 1 by 2 times of A plus A transpose plus 1 by 2 times of A minus A transpose, where 1 by 2 into A plus A transpose is symmetric and 1 by 2 times of A minus A transpose is skew symmetric. Okay. Now again, let us say if we are having a matrix, right? Let's talk about this question. Given the matrices J is equals to 3, 2, 1, 4, 2, sorry, 2, 4, 2, 1, 2, 6, and K is 1 to negative 1, the product of K transpose JK. So this was asked in 2014 for civil. Right. So how to solve this? So there is K transpose J and K. So if I'm multiplying the first two, so then what do we get? So that is 3 plus 4, 7 minus 1, 6. 2 plus 4, sorry, 2 plus 8, 10 minus 2, that is 8. 5 minus 6, that is negative 1. And that is 1 to negative 1. And the value is 6 plus 16 plus 1, which is 23. Right. Yeah, here is the question, guys. Again, this was asked for civil. So the minimum number of multiplications involved in computing the product PQR, where P has 4 rows and 2 columns, Q has 2 rows and 4 columns, R has 4 rows and 1 columns. So PQR, we can obtain this PQR in two different ways. As I said, matrix multiplication is associative, P times of QR and PQ times of R, right? Now, if I look into the first case, that is P times of QR. Now, first, if I evaluate Q, which is of order 2 cross 4, R is of order 4 cross 1, then number of multiplications needed to compute the product is M into N into P, right? So here it will be 2 into 4 into 1, and that is equals to 8. And say the result is A, which is of order 2 cross 1, and P is of order 4 cross 2, then number of multiplications are 4 into 2 into 1, which is again 8. So total number of multiplications are 16. And if we look into the second case, that is PQ into R. So P is of order 4 cross 2 and Q is of order 2 cross 4. Then number of multiplications are 4 into 2 into 4, which is 32. And say the result is B, it will be of order 4 cross 4 and R is of order 4 cross 1. So 4 times of 4 times of 1, which is 16, and that is equals to how much? 48. So 16 is the minimum number of multiplications and 48 is the maximum number of multiplications. So 16 is the right answer. Now again. So let's come back to this later. Right. Now, this is about your the questions on the product, how the questions will be asked on the product and on the symmetric and skew-symmetric matrices. Right. Now, coming to the next topic, that is your determinants. Guys, are you there? Today, you people are being very silent.
No, sir.
Okay, right. Now, I think you people know how to find out the determinant and all. So just let me write a quick notes on the determinant. Like say if I'm having a matrix A is equals to A, B, C, D, then the determinant of A is given by AD minus BC, right? And again, if we are having, or if det A is equals to 0, then we say the matrix A is what? We say the matrix A is, sorry, singular matrix. And if det A is not equals to 0, then A is a non-singular matrix. And again, det A to the power n or det A is always equals to det A transpose. And det A to the power n is equals to det A whole to the power n. and determinant of AB is, can anyone? Yeah, determinant of AB, right? So that is det A into det B. And again, when we say uh, determinant of IN, what is determinant of the identity? No, Balaji, the determinant of identity is 1. Right. Now, again, the determinant of triangular matrix. So, triangular, it can be either the upper triangular or lower triangular, or it can be a diagonal also. Then it is the product of principal diagonal elements. Product of principal diagonal elements. So this is the determinant of a triangular matrix. Like say, for example, if I'm having a matrix A as 1, 2, 3, 0, -2, 4, 0, 0, 3. So then its determinant is 1 times of -2 times of 3, which is -6. Now again, if we are saying if any two rows, if any two rows or two columns in the determinant are identical, then what is that value of det? Right. So then the determinant is 0. And again, if any row or any column in the det is 0, then the det value is always 0. And again, if any two rows, or two columns in the determinant are interchanged, then det is multiplied with what? Det is multiplied with -1. That's it. Now again, let us say if I'm having a symmetric matrix or a skew symmetric matrix, let us say if AN is skew symmetric, then det A is 0 if n is odd, and it is a perfect square if n is even. Remember, the determinant of a 3 cross 3 skew symmetric matrix is always 0. Okay? And again, the determinant of orthogonal matrix is plus or minus 1 always, and the det value does not change. The det value does not change even after applying elementary operations. Even after applying elementary operations without interchanging rows and columns. Without interchanging rows or columns. And again, one of the most important, which we'll be using regularly when we are solving the problems. Now, if each and every element of a matrix is multiplied with k, and if we are finding the determinant of that, then there is k to the power n into det. That means whenever a constant is coming out of the determinant, it will be taking the power as the order of a matrix. Okay? Right. So now let's solve this. So the matrix A has det 100 and trace 14. The value of modulus of A minus B. Now what is trace? So trace of A is given as 14. So that is A plus B plus 7 is equals to 14, or A plus B is equals to how much? 7. Now I hope everyone knows how to find out the trace. It is the sum of the principal diagonal elements. That we'll be calling it as trace. Now given det is equals to how much? Det is equals to 100. I'll expand according to the last row. Why? Because all are zeros, so I'll be getting only one. So that is b times of det of, take out the row and the column. That is A03251,002 is equals to 100. And again, I'll expand according to the last row. So that is 2b times of 5a is equals to 100. Then AB is equals to how much? 10. Now I want modulus of A minus B. But we have A plus B and AB. So then the relation between A minus B and A plus B is A minus B whole square is equals to A plus B whole square minus 4AB, right? And that is A plus B square, that is 7 square, minus 4 times of 10, and that is 49 minus 40, which is 9. So A minus B is what? Plus or minus 3. Then modulus of A minus B is 3. Right. Now, so the determinant of the matrix. And this was asked for 2 marks for civil as a fill in the blank. So now I'll make use of the property that the determinant of a matrix does not change even after applying elementary operations without interchanging the rows and the columns, right? Now, the first main basic point is the first element should be 1. Okay. So now what I'll do is I'll interchange R1 and R2. Now, if I'm interchanging R1 and R2, so then I have to multiply with negative 1, 1, 0, 3, 0, 0, 1, 2, 3, 2, 3, 0, 1, 3, 0, 1, 2. Right? Now, with this 1, you make the down elements as zeros. That means to R3, applying R3 minus 2R1, and to R3 again applying R3 minus 3R1. So that is minus 1 times of det of 1030 0123 0 3 minus 2, that is 3, 0 minus 6 1 minus 0, and again 0 0 1 minus 9 minus 8 2 minus 0. Now take out the first row and the first column. So that is minus 1 times of minus 12 plus 8 minus 4, minus 2 times of 6 minus 0, plus 3 times of negative 24. So minus 4 minus 12 minus 72. And that is equals to how much? This is 84, 88. Now here, there's a question asked in the year 2015 for CSC. Hmm. So how to solve this? So now first multiply the matrix A. That is 2, 18, 10, negative 4, negative 36, negative 20, 7, 63, 35. Now I told you, you can take a constant from any row or any column. Now if I'm taking 2 out of the first row and negative 4 out of the second row and 7 I can take common from the third row. So that is 2 times of negative 4 times of 7 det of. So in the first row if I'm taking 2 common, that is 195, and again minus 4 common from the second row, it is 195, 7 common 195. Now if any two rows or two columns in the determinant are identical, then the det value is 0. Right. Hmm. So perform the following operations on the matrix. Add the third row to the second row. Subtract the third column to the first column. Then the determinant that is obtained is now, if you remember, the determinant of a matrix does not change even after applying the elementary operations, right? So that means even though how many operations are applied, the determinant doesn't change, right? Now from the third row, from the third column, we can take 15 common. So if I'm taking 15 common from the third column, That is 3, 7, 13, 4, 9, 2, 3, and 15 if it goes out from 105, that is 7 and 13. So the two columns are identical, then the det value is 0. Right. So this is a question. Given the determinant of a matrix 130264 negative 102 is negative 12, the determinant of this matrix is. Now, if you look into this matrix, it is 2 times of A, right? So it is 2 times of A. So that means det of 2A. Now I told you when you are taking 2 out of the determinant, then this 2 will be taking what? It will be taking the power as no, Joshi. So 2 cube into det A. That is 8 times of negative 12, which is negative 96, option A. So det of Ka is what? K to the power n into det A. Right. So if A and B are two square matrices of order 4, such that det A is negative 2, det B is 5, then det of 4AB. Can anyone? Right. Perfect. It is negative 160. Now, if 4 is out of the determinant, it is 4 to the power 4. Is it negative 160, Balaji? Are you sure? No. Balaji didn't. Joshi has answered. Right. So, 4 to the power 4 into det AB. Right. So, now 4 to the power 4, 16 16s, 256. Into det A into det B. And that is 256 into det A is negative 2, det B is 5, which is negative times of 2560. Right. So for A is equals to 1 tan x negative tan x 1, the determinant of A transpose into A inverse. Can anyone? So no need of finding anything. So directly by using the properties you can solve. Det AB is what? Det A into det B. And det of A and A transpose are always same. Right? Into det A to the power minus 1. Det A to the power n. And det A into det A to the power minus 1 is 1 by det A. So det A into 1 by det A is 1. That's it. Now, so coming to the next concept, that is the rank. Now, we can define the rank of a matrix in 3 different ways. So the first way of defining the rank of a matrix is the number of linearly independent rows and columns gives the rank. And another way of defining is it is the highest non-zero or the highest order. Let's write in this way. The highest order of a non-zero minor of a matrix. So highest order of a non-zero minor of a matrix gives the rank. And the third way of defining the rank is the number of non-zero rows in echelon form. Gives the rank. So the number of linearly independent rows or columns gives the rank, or the highest order of a non-zero minor of a matrix gives the rank, and the number of non-zero rows in echelon form gives the rank. Now, what do you mean by this echelon form? So we can define a matrix is in echelon form as if it satisfies two conditions. So the first condition is zero rows, if any, must be below all non-zero rows. And the second condition is number of zeros before the first non-zero entry before the first non-zero entry in each row must increase down the rows. So if a matrix satisfies these two conditions, then we can say it is in echelon form. And if I'm putting one more condition that the first non-zero entry in each row is 1. So then we say it is a row echelon form. Okay. So if a matrix is satisfying only the two conditions, so simply we say it is an echelon form. And if it is satisfying the third condition also, then we say it is in a row echelon form. Now again, if you look into the properties of this rank of a matrix, right. Now, if we look into the properties of the rank of a matrix, so the first property, what we'll be saying here is rank of a matrix is always greater than or equals to 1. That means rank cannot be 0. and rank is 0 if and only if A is a null matrix. If A is a 0 matrix, then only the rank is 0. And the rank of A, m cross n, is less than or equals to minimum of m and n. And rank of AB is less than or equals to minimum of rank of A and rank of B. And rank of A is always equals to rank of A transpose. So that means A and A transpose, they always have the same rank. And rank of IN is N. And the most important one, if A is a square matrix of order n, and if deta is equals to 0, then we say rank is strictly lesser than n. And if deta is not equals to 0, then rank of a matrix is exactly n. And we'll be looking at this property in a reverse direction also. Like whenever the rank of a matrix is less than n, then the det value is 0. And whenever the rank of A is equals to n, then det is not equal to 0. So we'll utilize this point in reverse direction also. And if all the entries, or if all the elements in a matrix are same, then the rank of that matrix is exactly 1. No matter what, whatever the order of that matrix is, so the rank of that matrix is always equals to 1. Okay, right. Now, so find the rank of the matrix. So just simply apply the operations. So by using this 6, make the down elements as zeros. So that means to R2 applying 3R2 plus R1, and to R3 applying, so 21. Or we can do in this way, 7 and 3. So that is 3R3 minus 7R1. So then that is equivalent to 60440. So this is 42. 24 plus 4, that is 28. 18 threes, 54 plus 4, 58. And this is 0. Negative 14 times of 3, that is 42 minus 0. 0, this is negative 28. Minus 30 minus 28 minus 58. And again to R3 applying R3 plus R2. So then that will be 6044 042 28 58 0000. So what is the rank of the matrix? So the rank of the matrix is 2. Right. Now again, so let A is equals to Aij, where 1 is less than or equal to I, less than or equal to j, sorry, n. with n greater than or equals to 3. That means the order of the matrix should be greater than 3. Aij is equals to I into j. Then the rank of the matrix is. Now let's take n is equals to 3 and we'll write the elements of the matrix. So how do we write the elements of a matrix? Generally A11, A12, right? So how the elements are? Product of their positions. So 1 into 1, A12, A13, A21, A22, A23, A31, A32, A33. Now, if I apply the operation, so that is to R2, R2 minus 2R1 and to R3, R3 minus 3R1. So obviously the second row and the third row will become 0. So you'll be left with only one row. So the rank of the matrix is 1. Now, so this is a question asked for EC in 2007. And this is the first question in my career that I have seen a 2 marks question on rank of a matrix. Okay. So you just try. Your answer is 4. Okay. Now, so if rank of 5 cross 6 matrix is 4, then which one of the following statement is correct? Q has 4 linearly independent rows and 4 linearly independent columns. Q has 4 linearly independent rows and 5 independent columns. Q into Q transpose is invertible. Q transpose into Q is invertible. Now, which is the correct one? Any guesses? So option A is the right one. Now, so if A is m cross n, full matrix with m greater than n, and I is the identity matrix, let A plus is equals to A transpose into A whole inverse into A transpose. Then which one of the following statements is false? Hmm? So now when I'm having A plus is equals to A transpose, A whole inverse into A transpose. Or this can be written as what? A inverse, A transpose whole inverse into A transpose. And that is equals to what? A inverse and A transpose whole inverse and A transpose. This is I. So I'm getting A plus is equals to A inverse. So that implies A into A plus is equals to the identity. So first one is true. And coming to the second one, or yeah, C is true. And A into A plus whole square is A into So even B is true. And we are stuck with A and D. So A into A plus into A is equals to A. Now A into A plus is I into A, which is A. Obviously it is true. So D is a false one. Right. So this is the proof of C. This is a proof of B. This is a proof of A. Right. Now again. So coming to the linear system of equations. Now, as I said, there are two types of linear system of equations. One is what? One is a non-homogeneous and another one is homogeneous. And when we talk about non-homogeneous, so these equations are of the form Ax is equals to B and homogeneous Ax is equals to O, right? Now, when we talk about this non-homogeneous system of equations, so these equations, they have solution only if rank of A is equals to rank of augmented matrix. And they'll be having a unique solution if rank of A is equals to rank of augmented and if it is equals to n. And they'll be having infinite number of solutions if rank of A is equals to rank of augmented and if it is less than n. And no solution if rank of A is not equals to rank of augmented matrix. Okay? Right. Now, when it comes to the homogeneous, they always have a solution. They always have solution. And they will be having zero solution. They have zero solution if rank of A is exactly equals to number of unknowns. And this zero solution is also called as the trivial solution. Okay. And they'll be having a non-zero or non-trivial solution if rank of A is strictly less than n. And they'll be having so number of linearly independent solutions are given by what? N minus rank, where n represents what? N represents the number of unknowns. Okay. And again, if det an is equals to 0, then we said rank of A is less than n, then the system of equations will be having trivial solution. That means zero solution. If det an is not equals to 0, sorry, non-trivial, I'm sorry guys. So if det an is equals to 0, then rank of A is equals to n, then the system of equations will be having a trivial solution. That means a zero solution. Okay. So these are the points that to be noted in the linear system of equations. Now, if you look into the questions, so the system of equations has unique, infinite, no solution, exactly one, two solutions. So obviously, option D, it can't be your answer. Why? Because there is no question. The system will have either unique or infinitely many. There is no exact number of solutions. So now if we start solving these equations, so just find out the rank of the matrix that there is 2, 1, 3, 5. That means I'm writing the augmented matrix 1, 2, 5, 14. Right? So this is the augmented matrix A by B. So find out the rank. So that is to R2 applying what? 2R2 minus 3R1 and to R3 applying R3 minus, sorry, 2R3 minus R1. So then that is equivalent to 2, 1, 3, 5, 0. So 0, negative 3, 2, negative 3, negative 1, minus 8, minus 15, minus 23. 0, and this is 4 minus 1, 3, 10 minus 3, 7, 28 minus 5. 28 minus 5, that is 23. I think I made a mistake. 2 2's 4 minus, sorry, 2 minus 9. 2 minus 9 is minus 7, right? So now again, these two are identical. So then rank of A is 2 and rank of augmented is also 2 and it is less than the number of unknowns. So it is having infinitely many solutions. Right. So again, the number of solutions for this system. Okay. You guys just try this. And this is a question asked in engineering services exam. Now, if the options are given in this way, don't go on solve the system of equations. Just go in a reverse process. So that means go on substitute the values, check out for which values all the three equations are satisfied. Now, if I'm looking at A equals to 2, Y is 2, Z is 0. So that is 2 is Z plus 2, that is 4. First equation is satisfied. What about the second? 2 minus 2 plus 0. So that is 0. So second equation also satisfied. And this is 4 plus 2 plus 0, which is 6, which is not equal to 5. So option A is not the answer. And coming to the B option, X is 1, Y is 4, Z is 1. So that is 1 plus 4 plus 1, that is 6, which is not equal to 4. So B is also not in the answers. And coming to the third, there is 2 plus 4 plus 3, which is 7, 9, and that is not equal to 4. So then obviously D will be your answer. When all the three are not there, 1 plus 2 plus 1, which is 4, and 1 minus 2 plus 1, which is 0, and 2 plus 2 plus 1, which is 5. Right. So option D is the answer. So if the solution is given in the options, go with the options. Don't solve the system of equations. Okay. Right. So there is the one which was asked in 2019 for mechanical, and it was asked for 2 marks. So the system of equations has infinite solutions if A equals to. So now, as we are saying infinitely many solutions, so write down the augmented matrix. So that is 1, 1, 1, 1, A, negative A, 3, 5, 5, negative 3, A, and 6. So what are the operations? So to R2, applying R2 minus A R1, and to R3, applying R3 minus 5 R1. So then that is 1, 1, 1, 1, 0, minus A minus A, minus 2A, 3 minus A, 5 minus A, 0, minus 3 minus 5 minus 8, and A minus 5, and 6 minus 5, which is 1. Now again to R3, applying what? AR3 minus 4R2. And that is 1, 1, 1, 1, 0 minus 2A, 3 minus A, 5 minus A, 0, 0. Right. Now from here, everything will change. A into R3. That is A into A minus 5 minus 4 times of R2. That is 3 minus A. So that is A square minus 5A plus 4A. That is minus A and minus 12. And here A minus 5 times of 5 minus A. I think I made a mistake. A minus 4 times of, right. So this is A plus 4A, that is 5A minus 20. Now, as he said, infinitely many solutions. So that means these two should be 0. So that is 0 for A equal to 4. And this is 0 for which values? A equal to 3 and A equal to 4. Is it 3? I won't think. Minus 3. Right. So among these two, which is common? A equal to 4 is a common. Right. Now here is, these are few questions, okay? Just try from your end. If you have any doubts, just let me know. And I think most of the problems I have solved it in your class notes only. Even this problem is there in your notes, which I have explained to you. Okay? Right. Guys, can we have a 5 minutes break? Right. So just 5 minutes and we'll start with the eigenvalues and eigenvectors. Right. Are you guys there? Right. Now let's get started with these eigenvalues and eigenvectors. So if we look into the definition of eigenvalues and eigenvectors, now a matrix AN is any matrix and a non-zero vector X is said to be an eigenvector, is said to be an eigenvector if there exists a scalar lambda such that Ax is equals to lambda x. Then this lambda, we are calling it as what? Lambda, we call it as an eigenvalue. Lambda is the eigenvalue and x is the eigenvector. And always remember, the eigenvector is a non-zero vector. There is no chance that the eigenvector is zero. Okay. And when you look into the properties of these eigenvalues and eigenvectors, so the first property, or let us say, if I'm having a matrix of order 2 cross 2, then the characteristic equation of a 2 cross 2 is given by lambda square minus trace of A into lambda plus det A. And another one, like if A is a 3 cross 3 matrix, then the characteristic equation is lambda cube minus trace of A into lambda square plus sum of minors of principal diagonal elements into lambda minus det A is equals to 0. And when we are saying the eigenvalues, that means the trace of a matrix is always equals to sum of the eigenvalues. And the determinant of a matrix is always equals to product of the eigenvalues. So this is sum of eigenvalues and this is the product of eigenvalues. And if 0 is one of the eigenvalues, if 0 is one of the eigenvalues, then det A is always equals to 0. And you can use this property in a reverse direction also. That means if det A or if the determinant of a matrix is 0, then the 0 will be one of the eigenvalues. And the constant term, so the constant term in the characteristic equation is always the determinant of a matrix. And again, so the eigenvalues of triangular matrix are the principal diagonal elements. And eigenvalues of A and A transpose are always same. Or you can say they are always equal. And if A plus Bi is one of the eigenvalues, then A minus Bi is also an eigenvalue, is also an eigenvalue. And right. Now again, if we say, right, this is a 10th property. So the eigenvalues of symmetric or Hermitian are always real numbers. And the eigenvalues of skew symmetric or skew Hermitian are either zeros or purely imaginary. Purely imaginary. So they can be either zeros or they can be either purely imaginary numbers. And if lambda is one of the eigenvalues, if lambda is an eigenvalue of orthogonal, then 1 by lambda is also its eigenvalue. And what else we are having now? So when we talk about the theoretical ones, so now the problematic ones, if lambda is the eigenvalue of A, then eigenvalues of first one, A to the power m, is lambda to the power m, and A plus or minus ki is lambda plus or minus k, and ka is k lambda, and A inverse is 1 by lambda, provided det A is not equals to 0. And adjoint A is det A by lambda, again provided det A is not equals to 0. And one of the most important among all these 5 subpoints is A to the power m plus A1 into A to the power m minus 1 plus so on plus am minus 1 into A plus ami is lambda to the power m plus a1 into lambda to the power m minus 1 plus so on plus am minus 1 into lambda plus am. Okay, when you are solving the problems, so this is the main thing that we'll be using it. Okay, right. Now, let us say that is the 13th one, right? Now, let's go to the 14th. The eigenvectors of A and A transpose, sorry, A and A power m, A and KA, A and A plus or minus KI, A and A inverse, A and adjoint A. So their eigenvectors are always same. Their eigenvalues may differ, but their eigenvectors are always same. Okay, and the eigenvectors of A and A transpose are not same. Remember, A and A transpose have many things in common. They have the same determinant, they have the same rank, they have the same eigenvalues, but their eigenvectors are not same. Okay, and yeah, when it comes to electrical, this question has been asked many times. The eigenvectors corresponding to different eigenvalues of a symmetric matrix are orthogonal. So remember, we are talking about the vectors. Orthogonal means what? Like say if A is a symmetric matrix and it is having two eigenvalues, lambda 1 and lambda 2, and they both are not same. And for lambda 1, let us say x1 is the eigenvector. For lambda 2, x2 is the eigenvector. Then the eigenvectors corresponding to different eigenvalues of a symmetric matrix are always orthogonal. That means x1 transpose into x2 is equals to x2 transpose into x1. The product is always 0. Okay, almost 3 questions were asked on this note point, and all these 3 were asked only for electrical. Okay, so these are 16 properties of your eigenvalues and eigenvectors. Okay, now choose the right response for the question. Consider 3 cross 3 matrix with every element being 1. Its only non-zero eigenvalue is. Can anyone try? Hmm. Its only non-zero eigenvalue. Now what we are saying, all the elements of the matrix are 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. So if all the elements of a matrix are same, then the eigenvalues are 0, 0, and trace of a matrix. And that is 0, 0. What is the trace? That is 3. That's it. So 3 is the only non-zero eigenvalue. Now let us say if I am having the matrix A as uh, A, 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 and A, and A. Now, can you tell me what are the eigenvalues for this? What are the eigenvalues for that matrix? Right. The eigenvalues are 0, 0, and 3. Now, so consider the following matrix. The absolute value of the product of eigenvalues. So what is the product of eigenvalues? Find out the determinant. That will be the product of eigenvalues. Now, what are the operations to be applied? So to R2 applying, R2 minus R1. To R3 applying, R3 minus R1. And to R4, again the same, R4 minus R1. So then there is 1, 2, 4, 8, 0, 3 minus 2, 1, 5, 19, 0, 2, 12, 64 minus 8, 56, and 0, 4, 21, and what else? 125 minus 8, 117. Now again, sorry, we are finding the determinant, right? Now again with this one, make the down as zeros. So that means to R2 applying R2 minus 2 R, sorry, to R3. R3 minus 2 R2, and to R4 applying R4 minus 4 R2. Right, I think last second row, second element. R4 minus R1. Right. This should be 3. Thank you. Thank you, Balaji. Right. So now this has to be 3. Okay. So now, so what do we get? That is det of 1, 2, 4, 8, 0, 1, 5, 19, 0, 0, 12 minus 10, that is 2, 56 minus 38, 56, 38. So that is 18, 0, 0, 21 minus 15, 21 minus 15, that is 6, 117 minus 27, 57, that is 60. Now take out the first row, first column, second row, second column. So the determinant of this, so there is 120 minus 6 8 48, there is 104. And sorry, 108. So then that is equals to how much? 12 is the answer. Now, so the value of x for which the matrix has 0 as the eigenvalue. Now, if 0 is the eigenvalue, then what we can say? Det A equal to 0 according to the property. So find out the determinant, equate it to 0, you will get the value of x. And again, so two eigenvalues of a 3 cross 3 matrix P are 2 plus root over minus I is minus 1 is I, and 3. Now, according to the property, as we are saying 3 cross 3, then P should be having 3 eigenvalues. But we have been given only 2, right? So now, according to the properties, like if A plus Bi is the eigenvalue, then A minus Bi is also the eigenvalue. So that means 2 minus I is also the eigenvalue. So he's asking to find the determinant of P, which is the product of the eigenvalues. And that is equals to 3 times of 5, that is equals to 15. Right, so this is asked in the year 2012. So let A be a 2 cross 2 matrix with the elements. What are the elements? A11 is 1, A12 is 1, A21, A22. So then the eigenvalues of A to the power 19. Now what is the characteristic equation of this? Lambda square minus trace is 0, right? And det -1 -1 -2. So lambda square is equals to 2. So lambda equals to plus or minus 2, root 2. So the eigenvalues are root 2 and negative root 2. So I want the eigenvalues of A to the power 19. So that is root 2 to the power 19 and negative root 2 to the power 19. And that is equals to how much? We can write it as root 2 into root 2 to the power 18. So 2 square will be gone, 2 to the power 9. So there is 2 to the power 9 into root 2. And again here negative 2 to the power 9 into root 2. So 2 to the power 9 is how much? 2 to the power 5, 32, 2 to the power 6, 64, 2 to the power 7, 5 and 2. Right, so that is option D. Now here, consider a non-singular 2 cross 2 square matrix A. If trace of A is 4, trace of A square is 5, the determinant of A is. Now let us say lambda 1 and lambda 2 be the eigenvalues of A. Now what do we have? Trace of A is 4. There is lambda 1 plus lambda 2. And trace of A square is 5. That is lambda 1 square plus lambda 2 square. So we want determinant of the matrix. So what is the determinant of a matrix? It is the product of eigenvalues. That means if I find lambda 1 into lambda 2, then I'll be getting my required one, right? So now can we write lambda 1 plus lambda 2 whole square? I think Balaji has answered. It is 0.5 Balaji. I won't think so. That is 4 square. So if we expand it, lambda 1 square plus lambda 2 square plus 2 lambda 1 lambda 2 is 16. And this is 2 lambda 1 lambda 2 is 16 minus 5. So lambda 1 into lambda 2 is how much? 11 by 2, which is 5.5. You have written only 0.5. Yeah. Okay. Let the eigenvalues of a 2 cross 2 matrix are 1 and minus 2, and the eigenvectors are x1 and x2. So the corresponding eigenvalues of a square minus 3a plus 4i and vectors also. So what is the eigenvalue for this? Lambda square minus 3 lambda plus 4. So for lambda equal to 1, so that is 1 minus 3 plus 4, which is 2. And for lambda equal to negative 2, so it is 4 plus 6 plus 4, that is 14. And we are stuck with A and B. Now we know that the eigenvalues of A and A power m, A to the power 2m or A to the power km, Ka, A inverse, adjoint A, their eigenvectors are same. No matter what, whatever the operations you are having, its eigenvalues will differ, but its eigenvectors are always same. So option A is the right one. Now, right. So there are few more questions in this. Okay. So I'll leave these questions for you to practice in the last moment by using all these properties. Okay. Right. So is there anything from your end in what we say in the linear algebra? Okay then. So if no doubts are there, so we'll wind off the session. And in the next session from 7, we'll be having what we say probability and stats. Okay. Right, guys. So we'll meet at 7 o'clock. And if you have any doubts, do ask me. So still we are having 5 more minutes to go. If you have any doubts, so I'll be here to clarify your doubts.